and welcome to another tacc system introduction. This is a webinar series where we introduce our clusters, their hardware, their respective file systems, and by the end of the webinar, users will know how to run their very first job on tacc systems. Today, we'll be going over a machine called Vista, currently our largest GPU HPC cluster. This is a National Science Foundation funded project, and we have users from all across the world working on this machine. If you would like to follow along at home, we'll be going over tacc documentation of the Vista user guide. So let's get started. At the top of the user guide, you will see notices. This is where we post things like maintenance windows or software updates that users need to know about. The next section is an introduction that explains the purposes and goals of the Vista HPC cluster. This section also explains that Vista is an ARM-based system and goes over the benefits of the Grace Hopper superchip. Finally, Vista is funded by the National Science Foundation. Please reference tacc when providing any citations in your work. Now, on to the next section. Whenever we talk about a modern HPC system, we're primarily talking about dozens, hundreds, sometimes even thousands of different computers linked together, each individually called nodes. These nodes all have different roles inside of the cluster. Some of them are login nodes, which is how you connect to the cluster from your local machine. Some of them are storage nodes that manage data. But a majority of the nodes inside of the cluster are compute nodes. In Vista, there are two types of compute nodes: Grace, which are pure CPU, or Grace Hopper nodes, which host one Grace ARM chip and one NVIDIA H200 GPU. These connect to the storage nodes, which are a vast file system that host users' home and Scratch directory. The compute nodes and the storage nodes are connected via Mellanox NDR technology, capable of 400 gigasecond uplink and download transfer. Now let's take a moment for a more in-depth look at these compute nodes. The first thing that users need to know is that this is ARM architecture. So when compiling your software, you need to ensure that it is designed for ARM architecture rather than traditional x86. The Grace compute nodes, as indicated by their name, have two Grace chips on them, totaling 144 threads per node, and have 286 gigabytes on their temp partition for users to use. The Grace Hopper nodes only have one Grace chip. However, they also have an NVIDIA H200 GPU and also have the 286 gigs on temp for users to use. Vista's login nodes are Grace nodes with 72 cores per Grace chip, and the network, as previously mentioned, is Mellanox NDR. For the Grace nodes, we use breakout cables that split the 400 gigasecond capability into 200 gigasecond for the compute. These connect the compute nodes to the home and Scratch file systems. Let's talk about file systems a little bit more now. Vista users have access to three network file systems. The first one we're going to discuss is the user's home directory. This is 23 gigs and is not intended for I/O or high-density file operations, but this is backed up regularly. So anything that's vital to your workflow should be saved here. Users also have access to the Scratch file system. This is intended for high I/O and read-write while running your jobs. There's no quota here, but this is not backed up and is subject to tax purge policy. Finally, users do also have access to a Lustre file system known as Work. Work is not backed up either, but it is never purged. It's 1 terabyte of storage space for users to store large data sets. Again, work is not intended for I/O, but it's recommended that users store their data sets here and then transfer them to the local/temp partition before running their jobs. The next part of the Vista user guide goes over accessing the system. But before you can access the system, you must be a part of an active allocation. In order to get an allocation on Vista, someone who is PI or Principal Investigator eligible has to request system time. This is someone who's faculty, staff, or a postdoctoral researcher in the United States. Once you are a part of an allocation, you can access the Vista system. There are multiple ways to do this. One method a lot of our users like to use is the tacc analysis portal, or TAP. You can find that at the URL below. In today's tutorial, we'll be going over accessing the system using terminal. So what I'm going to do is open a local terminal on my machine, and I'm going to type the command SSH for secure shell with my username @vista.tacc.utexas.edu. Then I'll be prompted for my username password, which nothing will type in as you type your password, so you have to know you have it correct. And then my tacc token code, which I'll find on my Duo multi-factor authentication. As soon as you log in, you'll notice a few things. One, we have updates to the system listed by date. In addition, you see the respective file systems that you have access to and your current usage and quotas. Finally, you'll see tacc tips. That's one of the modules that's already loaded on the system when you log in. And we'll go over modules later when we hit the LMOD section. When first logging into Vista, the default shell is set to bash, or the born again shell. If you would like to change your shell to a different type, please submit a ticket with tacc help desk and we can get that changed for you. Now that we're logged in the system, it's time to start talking about software. At tacc, we use something called LMOD, a module system that was developed and maintained at tacc. It makes it easy to manage your environment and gives users access to different software and different versions of those software packages. We're going to be using our diagnostic tool, Checklist, as an example for how to use LMOD. So, as you can see, I'm logged in and I'm going to run the command module list. This has all of my currently loaded modules on the system. Now, I'm going to run the command of module load checklist. And checklist is just a simple diagnostic tool that checks account level issues. So if I do module list again, you'll see that I have checklist listed now. And let me just highlight that real quick so you can see it. So now that that's there, I'm going to run the command checklist. And again, this is just going to do account level diagnostics, quotas, permissions, SSH keys, things like that. And if I want to unload a module, it's as simple as module unload checklist. Running the command again of module list, you'll see the checklist is no longer loaded into my environment. Now that's not all that LMOD can do. We have a lot of software packages available at tacc. They can be found here at this list of module avail. And you can see that some of these have different letters next to them, D being for default, L being for loaded, and G meaning it was compiled for a GPU. We also have this list available at the page of tacc software, where you can search by software package and check system by system and version by version. Seeing all of the available modules is not all that you can do with LMOD. You can use the command module spider to look for more specific information about different software packages. So let's try module spider NVIDIA for this example. And you'll see that this lists all the different versions of the NVIDIA module that we have. In addition, let's try to get a little bit more complicated. Let's say that we want to use a certain version of Python. We can look for module spider Python. And from here, you'll see one of the possible versions is Python 3.11, and all of the dependencies that you'll need to load with module load to make Python 3.11.8 work. So for doing this example, I'm going to run module list. So you see Python is not loaded. I'm going to run the command module load Python 3, which will fail because I don't have GCC or CUDA loaded. I'm going to look at module spider and look at the Python 3 requirements, seeing that I will need GCC and CUDA. And from here, I'll do module load GCC, followed by module load CUDA. And you'll see that they're both in my environment now when I run ML for module list. Then module load Python 3. And now I do have Python 3 active in my environment. Before we move on to running jobs on Vista, we're going to take a brief moment to discuss cron tabs. Users are allowed to start cron jobs and cron tabs on tacc login nodes, but it's important to note that they are unique to the login node that they are created on. If you want to check up on your cron tab, you just need to change your SSH command from SSH username at Vista to, for example, SSH username at login2.vista.tacc.utexas.edu. And once you type in your password and MFA token, you'll see that you are on login 2. So we're about ready to run our first job on Vista. But before we do so, we need to go over the production queues really quick. For Vista, it's fairly straightforward. There are two main production queues, Grace Grace and Grace Hopper. If you do not need a GPU for your job, the Grace Grace queue is for you. If you do need a GPU for your job, then the Grace Hopper is where you want to run. You'll notice that these two queues have different charge rates per node hour. This charge rate is determined by power usage, demand, and several other factors. And this charge rate is how we determine the number of service units, or SUs, that your job uses. SUs are how we handle accounting at tacc. In order to find the formula for SUs that your project will be billed, it's number of nodes times job duration in wall clock hours times the charge rate of the node per hour. Now that we've been over that, let's start our first job at tacc with an iDev job, or interactive development. It's important to remember not to run on a login node. Login nodes are shared resources, and running a job on them might impact other users' performance. So instead, we run on a compute node, whether that's Grace Grace or Grace Hopper. As you can see, I'm currently logged in to staff.vista, which is the tacc staff login node. I'm logged in as myself, M. Collins, and I'm currently in my home directory. As I said, you never want to run a job from the login node. So I'm going to run a command called iDev and press enter. This is going to do a few account checks really quick, and it's going to begin looking for an open development node that I can run my job on. And as you can see, I'm now on 642082, which is the name of this Grace Hopper node. From here, it's pretty standard command line interface to develop your code. I can run things like echo hello world, or I can do more intensive for loops with sequences, commands, and run iterations of command line that I need to do for interactive development. Since I'm the only user on this node, this won't impact any other users or their workflow. And here I'm just doing a very simple for loop command to show off basic command line interfaces via an iDev job. And I missed a little bracket there. So from here, I also want to run a job that I've written in the past. Currently, I'm in the home directory. It's also important to remember, not only should you not log in on login nodes, you shouldn't run anything from home. So I ran cds to change to my Scratch directory, and I have this coinflip.sh, which is just a simple coin flip bash script that runs a sequence 100 times and puts out the results. So since I'm now running from scratch, I'm going to go ahead and execute this bash script and run coinflip.sh. And as you can see, we have a sequence of 100 results of either heads or tails depending on what the randomizer decided. Since I'm also in my Scratch directory, I can go ahead and redirect this command to create files if I need to. So if I do coinflip.sh and redirect that to a file that let's call it results.txt. Oh, I guess I should put the date too. And it is 2026. .txt and hit enter. It'll just go ahead and create that file, and I'll have the results there. And it's really this simple to run jobs at tacc. All you need is a little bit of coding and an allocation to get this up and running. And to end the IDEV session, I'll just press exit, and then I'm back on the login node. So now we've learned how to do an interactive session. But what about whenever you know your code will run successfully and you just want to submit your job and be able to walk away? The IDEV queue only allows runs for about 2 hours, and sometimes your code could take up to 2 days to run. In that case, you're going to take advantage of Slurm, our job scheduler, and you'll create an sbatch script. An sbatch script is a simple script that allows Slurm to interpret your job parameters. We have an example on the Vista user guide. As you can see, it's a simple bash script with a series of arguments for Slurm to interpret. The first one here is -j, which is a job name to help you organize your files. An output file for your I/O. A time variable, which we highly recommend that you set your time only to what your job will need. A uppercase N for number of nodes. A small case n for total number of tasks per node. A partition with the -p. So, as I said earlier, if you don't need a GPU, Grace will work. Or if you do need a GPU, then the Grace Hopper queue. And finally, a -a for your allocation. It's important to set this, otherwise your job will not run. In our example, there are only a few other things that are kind of variable to what a different user might use, but the most important one is at the bottom, where it's IB run your code, and you replace it with your executable. So now let's look at an sbatch script that'll use the coinflip.sh that we used earlier in the IDEV session. As you can see, I have the -j set to coinflip %j. The %j will be the associated job ID that Slurm will issue our job. Then I have -o for the output file. I've added -e, and that'll create an error file for any errors that my job might experience while running. I follow that up with the -t, since I know this job will take less than 5 minutes to run. And I'm only going to be running this on one node. I have 8 tasks set for this job, though it won't take that many. The partition selected is Grace, since I won't be needing a GPU. I have my allocation set, and I've added 2 additional sbatch flags that'll email me when the job starts and when the job finishes. From there, it does look a little different from our example, because I've changed this to be set up for this coinflip.sh code. I have module list so that the output file will list all of the modules I have loaded, present working directory, and the date, so that I'll have all the information I need for this job. I do highly recommend creating an error file in case you need to do any troubleshooting. And then from there, on the final line, I have bash and the full path to coinflip.sh. I do highly recommend using full paths. And in this example, I use bash. Now, if you're using more than one node, you'll want to use IB run. So now let me show you how to submit your job to the queue with the sbatch command. As you can see, I'm on the login node in my Scratch directory, and I have the coinbatch.sh here. I'm going to use the command sbatch coinbatch.sh. You'll see an output of Slurm verifying a few things in my account, and then I'm going to run the command sq-u and my username, and you'll see my job in the Slurm queue. It has a job ID on the grace partition. Under ST, that's its state for pending, which means the job has not started yet. Through some movie magic, we're going to fast forward, and you can see that the state has changed to CG for completing. Whenever I run SQ again, the job is completely out of the queue, and you can see my error and output files from the job. Then once I run less on the output, you can see the results of my job. And that's how we run jobs on tacc systems. I'd like to thank you for joining us for this Vista system introduction. There are a few things that we didn't go over, as they might not be applicable to all users. I would highly suggest reading over the Vista user guide. We have additional instructions for things like building third-party software, additional Slurm commands, or using NVIDIA's multi-process service. Thanks again for being here.